So we've talked about acid-base theory as regards organic chemistry a little bit before, but there's one more piece that we need to define in addition to what we've done already, and that's really to talk about the general theories of acid-base. So in general chemistry, you may have started with the Arrhenius definition of an acid, which is to say an acid is something that dissociates when placed in water to give H plus or hydronium, and by contrast, of course, a base is something that dissociates in water to give hydroxide ion. And that's fine as far as definitions go, but it's fairly limiting for the purposes of organic chemistry, not least because the solvent implied is always water. And secondly, this is really talking about a compound reacting with water. And so we've already talked about how organic chemistry is more interested in compounds reacting with each other in the absence of water. So a Bronsted-Lowry definition of an acid is a far more powerful one. It's a more general one that applies for the purposes of organic compounds. And the idea is that an acid is simply any molecule that can donate protons, and a base is any molecule that can accept protons. And so I've drawn HCl in this relatively suggestive way where the proton part of it is in blue, and what we really have here is something that can accept a proton. Cl- is perfectly happy to exist as its conjugate base, the Cl-, but it can also accept a proton and exists as HCl. Likewise, hydroxide is something that's perfectly content to be a proton acceptor, which is why we consider it to be a base. In fact, if you mix together this base with HCl, you get full and complete reaction to form water, the conjugate acid of OH-, and you also get the Cl-. And again, the idea is proton donor is an acid, so therefore HCl is a acid. But if you look at water in this way, you can see both a proton and a proton acceptor. So water itself is an acid. And so we talk about this being the conjugate acid of hydroxide, the base, or perhaps you could talk about the conjugate base, chloride, of an acid, and so on. So really, if you're talking about conjugate acids and conjugate bases, that's a Bronsted-Lowry way of thinking about things. And the reason why we care is because we have now removed the necessity of doing this in water, and we've started to generalize. But actually, we can generalize even further. Now let's think about this reaction in terms of the electron flow that I tend to like to draw. So here's a hydroxide. It is going to go ahead and make a bond. Again, it's a proton acceptor, so it comes and takes this proton. This is the proton donor, so this is the acid. So it pulls off this hydrogen and pushes electrons onto the chlorine. This is the organic way of depicting the reaction, and we could choose to have our acid definition be in terms of the movement of protons, but that again is limiting in the same way that thinking only in terms of water is limiting. What if instead we started thinking about electrons being the interesting thing? So maybe a base is a donor of electrons. Maybe hydrogen is an acceptor of electrons. Said another way, can we get this to align more closely with the MO picture that we're already thinking about? I've already drawn out the reaction in these terms before, but the hydroxide has electrons in the highest occupied molecular orbital. This can serve as a nucleophile. It goes looking for a nucleus to bound with, an area of plus to bind with. Meanwhile, this thing here has places to put electrons in the lowest unoccupied molecular orbital, in this case the HCl Sigma star. This is our electrophile. And wouldn't it be interesting if we could have an acid-base definition that is more appropriate for organic molecules because it doesn't rely on protons, but instead is thinking about the electronics involved. And in fact, that's precisely what Gilbert Lewis, inventor of Lewis structures, came up with at nearly the same time as Bronsted and Lowry were developing their theory. What if we generalize this completely? What if we generalize this to the case of organic molecules? What if instead of thinking in terms of protons, because plenty of organic molecules don't have protons that are available to be donated or accepted, what if we instead think in terms of the electronics of what's happening? The mechanistic flow, the electron flow. So in Lewis's definition, an acid is anything that can accept electrons, and a base is anything that can donate those electrons. And so a classic example of a Lewis acid would be something like BF3. There's no hydrogens anywhere. There's no H pluses to give at all. And yet, this behaves precisely as HCl does in the sense of how it interacts with outside electrons. So specifically, this boron has an empty p orbital sitting right here. It has an occupied molecular orbital, and in fact, boron in the third column of the periodic table is content. It is not charged without an octet. On the other hand, the octet rule is important. It wants to make an octet. So it wants to accept a pair of electrons. It has an empty orbital. A place to put those electrons. The LUMO here is this empty p orbit. Meanwhile, over here we have ether. Diethyl ether has lots of protons on it, 3 hydrogens, 2, 2, 3, but none of them are acidic. None of them are basic either. These hydrogens are bound to those carbons and they're not going in. On the other hand, this is a base in the terms of having too much in the way of electron density. Well, maybe not too much, but at least it has electron density that it can spare, electron density that it can donate. So in the highest occupied molecular orbitals, which are these oxygen lone pair, there's electron density that's available to be donated into the BF3. So what this ends up making is what we call BF3 etherate, and it is something that you can buy commercially. BF3 with ether around to donate to that empty orbital, and it makes both molecules quite content. There's good interaction there. In the sense where the oxygen is using its electron density to donate, it is serving as a nucleophile. Of course, boron in this case is the electrophile. The whole point of the little discussion about acid-base theory is that Arrhenius is too limiting for the purposes of organic chemistry. It must happen in water. And along those lines, Bronsted-Lowry is better. There are plenty of molecules that we can think about in Bronsted-Lowry term as donating protons and as accepting protons. But at the core of that proton donation and accepting idea is really electron flow. So if we want to generalize this even further, rather than thinking about the protons, why not think about the electron flow? Anything that can donate electrons into an empty orbital is a nucleophile, and a nucleophile is fundamentally a base. It is an electron donor. Anything that can accept electrons into an empty orbital is an electrophile, but that also makes it an acid. So fundamentally, base and a nucleophile are doing the same thing in the Lewis sense. They donate electrons. An acid and an electrophile are the same in terms of Lewis terms. They accept electrons. You'll see this much more as we go on to substitution chemistry. When we start talking about the differences between acids and bases, then this becomes a little bit more complicated. But the idea at the moment that I want you to take away is that anything that can donate electrons is a base and a nucleophile. Anything that can accept electrons is an acid and an electrophile.